Hello everyone, myself is Dinesh and my roll number is 536 and my topic is difference between graph traversals. Definition: a graph G V, comma E is a non-linear data structure that consists of node and edge space of objects connected by links. There are two types of graphs, that is direct graph and undirected graph. Direct graph, a graph with only direct edges is said to be direct graph, and undirected graph, a graph with only undirected edges is said to be undirected graph. Graph traversals. Graph traversal is a technique used to search for a vertex in a graph. It is also used to decide the order of the vertices to be reached in a search process. A graph traversal finds the edges to be used in a search process without creating loops. This means that in graph traversal, we can visit all the vertices of the graph without getting into a looping path. There are two graph traversal techniques. First one is DFS, depth first search, and second one is BFS. What is BFS? BFS stands for breadth first search. It is also known as level order traversal. The queue data structure used for breadth first search traversal. When we use the BFS algorithm for the traversal in the graph, we can consider any node as root node. Let's consider the below graph for breadth first search traversal. Suppose, and in the given graph we can see that, yes. Suppose we consider node 0 as a root node. Therefore, the traversing would be start from node 0. In the given graphs, we consider as a 0 as a root node and traverse from this vertex to all of the vertices. Therefore, traversing would be start from node 0. Once node 0 is removed from the queue, it gets printed and marked as visitor node. Once node 0 gets removed from the queue, then the adjacent nodes of node 0 would be inserted in the queue as shown below. The adjacent node of node 0 is 1 and 3, but we consider it as 1. So now the node 1 will be removed from the queue. It gets printed and marked as a visitor node. Once node 1 gets removed from the queue, then all adjacent nodes of a node 1 will be added in the queue. The adjacent nodes of 1 are 0, 3, 2, 6. As we can see, adjacent nodes of 1 are 0, 2, 3, 5, 6, and 5. But we have to insert only unvisited nodes in a queue. Since nodes 3 to 6 and 5 are unvisited, therefore these nodes will be added in the queue as shown below. The next node is 3 in a queue. So node 3 will be removed from the queue. It gets printed and marked as visitor as shown below. Once node 3 gets removed from the queue, then all adjacent nodes of node 3 except the visitor nodes will be added in the queue. The adjacent nodes of node 3 are 0, 1, 2, and 4. As we can see, the adjacent nodes of 3 are 0, 1, 2, and 4. Since nodes 1, 0 and 1 are already visited and node 2 is present in the queue, therefore we need to insert only node 4 in the queue. Now the next node in the queue is 2, so 2 would be deleted from the queue and it gets printed and marked as visited as shown below. Once node 2 gets removed from the queue, then all the adjacent nodes of node 2 except the visitor nodes will be added in the queue. The adjacent nodes of 2 are 1, 3, 5, 6, and 4. Since the nodes 1 and 3 have already been visited and 4, 5, 6 are already added in the queue, therefore we do not need to insert any node in the queue. The next element is 5, so 5 would be deleted from the queue. It gets printed and marked as visitor as shown below. Once node 5 gets removed from the queue, then all the adjacent nodes of node 5 except the visitor nodes will be added in the queue. The adjacent nodes of the node 5 are 1 and 2. Since both of the nodes have already been visited, therefore there is no vertex to be inserted in the queue. The next node is 6. So 6 will be deleted from the queue. It gets printed and marked as visited as shown below. Once the node 6 gets removed from the queue, then all the adjacent nodes of node 6 except the visitor nodes will be added in the queue. The adjacent nodes of node 6 are 1 and 4. Since the node 1 has already been visited and node 4 is already added in the queue, therefore there is no vertex to be inserted in the queue. The next element in the queue is 4. So 4 will be deleted from the queue and it gets printed and marked as visitor. Once the node 4 gets removed from the queue, then all the adjacent nodes of the 4 except the visitor nodes will be added in the queue. The adjacent nodes of the node 4 are 3, 2, and 6. Since the all since the all adjacent nodes have already been visited, so there is no vertex to be inserted in the queue. And another graph traversal technique is DFS. DFS stands for depth first search. In DFS traversal, the stack data structure is used, which works on LIFO, last in first out principle. In BFS, it follows FIFO, first in first out principle. In DFS, traversing can be started from any node, or you can say that any node can be considered as a root node until a root node is not mentioned in the problem. In the case of BFS, the element which is deleted from the queue, the adjacent nodes of the deleted node are added to the queue. In contrast, in DFS, the element which is removed from the stack, then only the one adjacent node of deleted node is added in the stack. Let us consider the below graph for depth first search traversal. It is the same figure example taken in the BFS. Consider node 0 as root node. First, we insert the element 0 in the stack as shown below because 0 is a root node. The node 0 has two adjacent nodes, that is 1 and 3. Now we can only one adjacent node, either 1 or 3 for traversing. 1 and 3. So suppose we consider node 1, therefore 1 is inserted in a stack and gets printed as shown below. Now we will look at the adjacent vertices of node 1. The unvisited adjacent vertices of node 1 are 3, 2, 5, and 6. We can consider any of these four vertices. Suppose we take node 3 and insert it in a stack as shown below. Consider an unvisited adjacent vertex of node 3. The unvisited adjacent vertices of node 3 are 2 and 4. We can take either of the vertices, that is 2 or 4. Suppose we take vertex 2 and insert it in the stack as shown below. The unvisited adjacent vertices of the node 2 are 5 and 4. We can choose either of the vertices, that is 5 or 4. Suppose we take vertex 4 and insert in the stack as shown below. Now we will consider the unvisited adjacent vertices of node 4. The unvisited adjacent vertex of node 4 is node 6. Therefore, element 6 is inserted into stack as shown below. After inserting element 6 in the stack, we will look at the unvisited adjacent vertices of node 6. As there is no unvisited adjacent vertices of node 6, we cannot move beyond node 6. In this case, we will perform backtracking. The topmost element, that is 6, would be popped out from the stack as shown below. As shown in the picture, we can see the topmost element in the stack is 4. Since there are no unvisited adjacent vertices left of node 4, therefore node 4 is popped out from the stack as shown below. As shown when node 4 is popped out like from 6 to 4. The next topmost element in a stack is 2. Now we will look at the unvisited adjacent vertices of node 2. Since only one unvisited node, that is 5, is left, so node 5 would be pushed down to the stack about 2 and gets printed as shown below. Now we will check the adjacent vertices of node 5, which are still unvisited since there is no vertex left to be visited. So we pop the element 5 from the stack as shown below. In this, we cannot move further 5, so we need to perform backtracking. In backtracking, the topmost element would be popped out from the stack. The topmost element is 5, that we would be popped out from the stack, and we move back to node 2 as shown below. From 6, from the stack, we can see that top of the element, first 6 is removed, and then 4, and then 2, and the unvisited node of 2 is 5, and 5 is also popped out, and backtracks to 2 if and sees if there is any unvisited nodes is left out. Now we will check the unvisited nodes of vertices of node 2, and there is no adjacent vertex left to be visited, so we perform backtracking. In backtracking, the topmost element, that is 2, would be popped out from the stack, and we move back to the node tray as shown below. Now we will check the unvisited adjacent vertex of node 3, as there is no adjacent vertex we left to be visited, so we perform backtracking. In backtracking, the topmost element, that is 3, would be popped out from the stack, and we move back to node 1 as shown below. From 6 to 4 and 4 to 2, and from 2 the unvisited node is 5, and again backtracks, and from 2 the unvisited node is 3, and and from 3 the unvisited node is 1. So after popping out the element 3, we will check the unvisited adjacent vertices of node 1. Since there is no vertex left out to be visited, therefore the backtracking will be performed. Then backtracking the topmost element, that is 1, to be popped out from the stack, and we move back to node 0 as shown below. We will check the element. We'll check the we'll check the adjacent vertex of node 0 which are still unvisited, as there is no adjacent vertex left to be visited. So we perform backtracking. In this, only one element, that is 0, left in the stack would be popped out from the stack as shown below. As we can observe in the above figure that the stack is empty, so we have to stop the DFS traversal here, and the elements which are printed is a result and DFS traversal. Differences between BFS and DFS. The following are differences between BFS and DFS. And first one is key definition. BFS stands for breadth first search, and DFS stands for depth first search. And second one is data structures. BFS uses queue to find the shortest spot. DFS uses stack to find the shortest spot. Source. BFS is better when target is closer to source. DFS is better when target is far from the source. Suitability for decision tree. As BFS considers all neighbors, so it is not suitable for decision tree used in puzzle games. DFS is more suitable for decision tree. As with one decision, we need to traverse further to augment the decision. If we reach the conclusion, we won. Speed. BFS is slower than DFS. DFS is faster than BFS. Time complexity. Time complexity of BFS is O big O of V plus C, where V is vertex and E is edges. Time complexity of DFS is big O of V plus C, where V is vertex and E is edges. That's it. Thank you, everyone.